Okay, so this is essentially a variable acceleration model, or a SUVAT model, whichever way we prefer to think of it, with vectors. Because we're in constant acceleration, we could use SUVAT. I tend to think that when you're in a vector world, it's just easier to do it by integration and differentiation, which is the way we're going to do it here. So we're going to start by saying that the acceleration is given by, and I'm going to do this in column form, is minus 1, 1. So we know that the velocity is equal to the integral of the acceleration with respect to time, which is going to give me negative t plus c and t plus d. Remember, you're going to need to include a constant of integration both in your I and your j components. Now, you're told that it is initially, that means when t equals 0, initially observed with a velocity of 2I. So we can say that v, given that t equals 0, equals 2, 0, and we've got our equation up here, which is minus, well, t was 0, minus 0 plus c, and 0 plus d. Now, it shouldn't be terribly difficult for us to work out, therefore, that c equals 2 and d equals 0, and so we've got our formula for velocity equals minus t plus 2, and here minus t plus 2, hopefully you can see that, and here we've got just t. Now, I could go on and do part A. Before I do that, I'm actually going to carry on, because we're on a roll, we're going to integrate again to find the distance. So we know that the position is the integral of velocity with respect to time. So we're going to integrate minus t plus 2, which is minus a half t squared plus 2t plus another constant, which I'm going to call k this time, and here I've got a half t squared plus L. And I know that the S, given that t equals 0, is equal to, it's got position vector of minus 2, so equals 0, minus 2. By equating those, we know, I'm not going to write it out in full, we know that this is 0, so I've got k equals 0, and here I've got L equals minus 2. K equals 0, L equals minus 2, which tells me that my formula for my position is S equals minus 0.5 t squared plus 2t and 0.5 t squared minus 2. So, once I've done that, it's just a matter of substituting in to find part A. Now, remember it's asking us for speed, so we're going to have to find the velocity first and then find the magnitude of the velocity. So, velocity at t equals 8 equals minus 8 plus 2 and 8, which is negative 6, 8. So, if we think about what it's doing, it's going 6 in the leftward direction and up by 8, so I don't have enough space to draw it accurately. If we think then the speed, which is the modulus of velocity, is going to be the square root of 6 squared plus 8 squared. Which is 10. Okay, looking at part B. We've got the distance when t equals, that should be when t equals 8. Distance when t equals 8 equals minus 0.5 times 8 squared plus 2 times 8, and 0.5 times 8 squared minus 2. So, 8 squared is 64, minus a half of 64 is minus 32 plus 16, gives me minus 16. 8 squared is 64, half of 64 is 32, minus 2 is 30. So if I look at my position vector, again, I'm going to be 16 to the left, and I'm going to be 30 above. And the distance here is modulus of s. It's going to be the square root of 16 squared plus 30 squared. And that's going to give me an answer of equal to 34 meters.